This roadmap walks through the skills needed to confidently design, operate, and secure a public key infrastructure. You'll see why PKI matters, how certificates work, how to protect keys, and how to apply PKI to real-world security challenges and future technologies. Public key infrastructure exists to manage digital identities and trust at scale. It governs how key pairs are generated, how certificate requests are submitted and approved, and how those certificates are issued, renewed, and revoked. This lifecycle underpins secure websites, VPNs, code signing, and many other security controls that depend on strong, verifiable identities. The certificate lifecycle starts with secure key generation, followed by creating a certificate signing request that binds a public key to identity data. After validation, a certificate is issued and used by clients and servers. Over time, certificates must be renewed before expiry, and if compromise or policy violations occur, they must be revoked so relying parties stop trusting them. A robust PKI relies on a hierarchy of components. At the top sits a highly protected root certificate authority, which signs one or more intermediate CAs. These intermediates issue certificates to end entities via registration authorities that validate identity information. Certificate revocation lists or similar mechanisms publish which certificates should no longer be trusted, allowing clients to detect and reject them. An X509 certificate is a structured document that binds a public key to a subject, such as a person, server, or device. It includes the issuer that signed it, the subject's identity, the embedded public key, and usage rules defining what it can do. Extensions like subject alternative names, key usage, and policy fields encode constraints that applications must honor. PKI supports a wide range of use cases. Web servers use TLS certificates to encrypt traffic and prove authenticity to browsers. Client certificates authenticate users or devices without passwords. Code signing certificates verify that software hasn't been tampered with. In the Internet of Things, device certificates uniquely identify hardware, enabling secure onboarding, updates, and telemetry across distributed environments. Hardware security modules, or HSMs, are dedicated devices that protect the most sensitive cryptographic keys. They generate and store private keys inside tamper-resistant hardware, enforcing strict access controls and audit trails. Organizations can deploy HSMs on-premises or rely on cloud-based HSM services, achieving compliant key protection aligned with standards like FIPS 140-2 or 140-3 for critical PKI operations. Within enterprises, PKI underlies secure remote access via VPNs, authenticated Wi-Fi using 802.11x, and strong user authentication. It also enables secure service-to-service communication, such as mutual TLS between microservices. Properly designed enterprise PKI becomes a foundational trust layer, allowing systems, devices, and users to authenticate and encrypt communication reliably across complex networks. Attackers target PKI through techniques like man-in-the-middle interception, where forged or misissued certificates trick clients into trusting imposter servers. Rogue CAs, certificate spoofing, and compromised registration workflows can all undermine trust. Studying real breaches demonstrates how poor governance, weak validation, or inadequate monitoring can allow attackers to issue fraudulent certificates with wide-reaching impact. Effective PKI requires strong governance and adherence to industry standards. Global frameworks define how public CAs must operate, while industry groups and regional regulations set expectations for validation, key protection, and incident response. Internal policies, audit controls, and documented procedures ensure that certificate issuance, management, and revocation align with regulatory requirements and organizational risk appetite. Leadership teams need a strategic view of PKI as part of a broader zero-trust approach. Decisions about which identities deserve certificates, how access is segmented, and how life cycles are automated directly influence security posture. When leaders understand PKI, they can support investments in automation, governance, and skills that reduce friction for users while hardening the organization against breaches. Developers benefit from hands-on experience with PKI building blocks. By standing up their own certificate authorities, integrating mutual TLS into microservices, and automating certificate management through modern protocols and APIs, they learn to embed security by design. This knowledge helps avoid hard-coded secrets, weak crypto practices, and ad hoc trust models in production applications. PKI is evolving to meet emerging challenges such as post-quantum cryptography, which aims to remain secure even against quantum computers. New models use verifiable credentials for privacy-preserving identity. PKI also supports large-scale IoT and AI ecosystems, where billions of endpoints must authenticate securely. Preparing now ensures infrastructures remain trustworthy as cryptographic algorithms and deployment patterns shift. Structured training helps teams move from theory to practice. Short executive workshops build high-level understanding, while intensive boot camps and deep practitioner programs develop hands-on skills. Curricula focused on cloud, automation, and zero-trust equip professionals to design and operate modern PKI. Formal certifications validate expertise, creating recognized benchmarks for architects, operators, and security leaders. Earning a PKI-focused certification demonstrates the ability to design architectures, manage certificate lifecycles, and align implementations with governance requirements. Certified practitioners can translate business needs into secure trust models, while architectural and governance credentials highlight capabilities in strategy and policy. Together, these roles ensure PKI remains resilient, scalable, and aligned with organizational objectives. Mastering PKI means understanding certificate life cycles, infrastructure components, and how cryptographic trust underpins modern security. By learning real-world applications, defenses against common attacks, and emerging trends like post-quantum cryptography, you can design and operate PKI that supports zero-trust strategies, secure development practices, and long-term resilience for your organization.